Today we are looking at circle geometry. Under circle geometry, we shall be looking at tangent to secant of a circle. Before now, we have looked at circle theorems. Circle geometry, we are looking at tangents and secants to a circle. We define a tangent to a circle as a straight line touching the circle at only one point. Here is the circle, center O, and here is the line ATB. The line ATB is touching the circle at the point T. So we say that the line segment ATB is a tangent to the circle center O. Now, OT, the line segment OT, is the radius of the circle, and it is perpendicular to the tangent ATB at the point of contact. Look at the point of contact with the radius and the tangent. The angle formed here is an angle of 90 degrees, which makes the line OT perpendicular to the line ATB. Take note of that. Let us now look at tangents from an external point to a circle. And in this case, the tangents from an external point to a circle are equal in length. What we mean is this. Here is the circle, center O. Here is the line QT, which is tangent to the circle. And the line PT, also a tangent to the circle. They are meeting at this point outside the circle. That's why we say external point. From this external point, a line was drawn to the circle and is a tangent to the circle. Now, at the center here, from O to Q and from O to P is the radii of this circle. Radii is the plural of radius. And of course, we have said that the radius is perpendicular to the tangent. And therefore, we have that a line from O to the external point T is a bisector of the shape formed POQT. And so we now have that this angle and this angle, they are equal. This angle and this angle, they are also equal, because the line OT bisects these angles. So in other words, 1, we have the line segment TP is equal to the line segment TQ. From T to Q and from T to P are equal. 2, the line segment OT bisects the angle at T and the angle at the center. This line OT bisects this angle, also bisects this angle. 3, the triangle OPT, OPT, that's triangle there, and the triangle OQT are what? Right-angled triangles. You can see that this is 90 degrees, this is 90 degrees, since the radius is perpendicular to the tangent. 4, by Pythagoras rule, which is very essential, key to solving problems of this type, using the Pythagoras theorem, because we have right-angled triangles involved. By Pythagoras rule, our OT squared is equal to OP squared plus PT squared. Where is OT? OT squared is equal to OP squared plus PT squared, which is the same thing as OQ squared plus QT squared. You can see them as illustrated in the diagram and in this illustration here. So you now see that by Pythagoras theorem, we can find the unknown side if we are given the necessary information. The angle between a tangent to a circle and a curve through the point of contact. We say that the angle between a tangent to a circle and a curve through the point of contact is equal to the angle in alternate segments. Now let's See this diagram here. Here is the tangent and here is a chord. A chord touches the circumference of a circle without necessarily passing through the center. If it passes through the center of the circle, it becomes a diameter. So diameter is a special chord. Now here is a chord, QT, and it's touching the tangent at this point. An angle is formed between the chord and the tangent. I will call it A1. Now the whole of this region is a segment. Then the alternate segment is this one. From here to this point is the alternate segment to this segment. So if there's an angle here formed, this angle will be equal to the angle P here, which is in the alternate segment. And this angle is formed by taking a line from the point of contact of that chord to the circumference, and then from that point also back to the end of that chord. It is this angle now that is equal to this. Similarly, you see this chord here, and then take this down here, and this down here. This angle here is equal to this one. So that is why we conclude, in this case, that the circle, the angle between the tangent to the circle, and the chord through the point of contact is equal to the angle in alternate segment. Take note of that. Questions do come from this area, and they are easily interpreted using this relationship. Intersecting chords. A straight line which cuts a circle in two distinct points is called a secant. Here is a circle, and here is a line cutting across the circle at both point A and point B. The line AB is called a secant. It's different from a chord. A chord ends at the circumference. A secant cuts across. Now, we look at two chords of a circle intersecting externally and internally at a point. We take the first case. Here is a circle, ABQP, and there is a external point. And this chord, when it ended here, it continued. So because it's from an external point, it didn't cut across like this. Take note. Neither did it do this. But it ended at point A and point P from the external point A, T. So these are two chords meeting externally. And then, of course, you will recall in our earlier discussion of circle geometry that angles on the same segment are equal. If you see now that BQ is a chord, and then this angle and then this angle, they are angles in the opposite segment, and therefore they are equal. Now, triangle ATQ, and triangle PTB are similar triangles. And because they are similar, the ratio of their corresponding side will be equal. Taking two of such ratios, AT all over PT is equal to TQ all over TB in the according order of similarity. Of course, we know that AQ is also all over PB. But now, we may do with these two, and this one is the same thing as saying, or if you AT ratio PT, remember that ratio is also what? Division. So this is division here, is also a ratio. So AT ratio PT equal to TQ ratio TB. And of course, if we cross and multiply, we now have AT times TB is equal to PT times TQ. These relationships are true. Okay, here is the internal intersection of two chords. Here is the circle APBQ, and you have the line AB and the line PQ. Both are chords, and they are intersecting at the point T. You observe that this angle and this angle are equal, and this angle they are also equal. They are the angles in the same segment. Now, triangle ATQ is similar to triangle PTB. This is your ATQ and this is your PTB. Since this angle and this angle they are equal, this angle and this angle they are equal, therefore the common angle here T is also equal in both cases. Hence, the triangle ATQ is similar to triangle PTB. In such a case, the ratio of their corresponding sides, in this case AT over PT, is equal to TQ over TB. And of course we know that AQ all over PB is also a ratio of their corresponding side. But we are limiting ourselves to these two, which will give us the result that we need now. So this can also be written as AT ratio PT equal to TQ ratio TB. Or by cross multiplication, AT times TB equal to PT times TQ. This is the eternal intersection. We have a third case, which is a special case. And this third case is the chord PQ becoming a tangent. So in this case, the chord PQ becomes a tangent. Now, if you look up, you have your PQ in the second one becoming a tangent here. And then the line AB meeting the point Q. You now realize that in this case, we have the same triangle, the triangle BPQ and triangle PAQ are similar. Here is your triangle BPQ. And then PAQ. This is PAQ. And we are saying that these two triangles, they are what? Similar. You recall that this angle here is equal to this angle. And then this angle here is also equal to this angle. So you are now able, this angle is common to the two triangles. And that is why we say they are similar. In this regard, our BP over PA is equal to PQ all over AQ. And it's also equal to BQ all over PQ. If we take these two cases, for example, you have that PQ times PQ, when you cross multiply, PQ squared is equal to AQ times BQ. So take note, PQ squared is equal to AQ times BQ. It's always a common question in our examinations. The transverse of common tangents to two circles. Here are two circles. Circle center O and the circle center C. Here is the transverse of the tangent, of the common tangent. This tangent AB is common to both this circle and this circle. So it transverses, cuts across them. Now, from the center O to the center C, there's a connection, a straight line connecting them. This now means triangle OAP similar to triangle CBP. This angle is 90, this angle is 90. Angle P is common, and therefore angle C and angle O here, they are equal. The radius of this circle, center O, is capital R. And the radius of this circle, center C, is small letter r. We now say that triangle OAP is similar to triangle CBP. OA all over CB is equal to AP all over BP equal to OP all over CP. And our OA is capital R and CB is small letter r equal to AP over BP equal to OP over C. Now where R is the radius of the circle, center O, and R is the small letter r is the radius of the circle, center C. We shall now use this A formation to solve problems. Example number 1. Here is a diagram described as follows. In the diagram above, PQRO is a straight line and PS is a tangent to the circle QRS with PS equal to SR. This means the length of PS is equal to the length of SR and the angle SPR is equal to 40 degrees. Find angle PSQ. Solution. We have here the triangle PSR. Triangle PSR is isosceles triangle. It's isosceles. In that case, our angle R is equal to 40 degrees. Base angles of a isosceles triangle. Hence, our PSQ, angle PSQ will now be equal to 40 degrees. Observe that the line QS is a curve and is touching the tangent here. So the tangent and the chord makes an angle, and this angle will be equal to the angle in the opposite segment. So this angle is equal to this angle. That is why we have the solution as 40 degrees. Example number 2. Here is a diagram described as follows. In the diagram above, PR is a diameter of circle PQRS. PST and QRT are straight lines. Find angle QSR. Solution. We have here the PRQ. Angle PRQ is equal to 30 degrees plus 35 degrees, and that is equal to 65 degrees. The reason for this is the exterior angle of triangle PRT. So this is the exterior angle of triangle PRT. Right. Our PSQ is also equal to 65 degrees. What is the reason? They are the same segment. Now our PR is a diameter. Our PRO is a diameter. Therefore, angle PSRO is equal to 90 degrees. Hence, we have that our QSRO, the angle QSRO, will be equal to 90 minus 65, and that is equal to 25 degrees. The required solution. Example number 3. Here is a diagram for you. Observe this diagram. From Z to T is a tangent, and this one is a curve from the external point to a circle. Okay. Now, in the figure above, TZ is tangent to the circle QPZ. Find X if TZ equal to 6 units and PQ equal to 9 units. Good. Your solution, remember the rule. ZT all squared to be equal to your QT times your PT. That is the rule. So our ZT is 6 squared, our QT is 9 plus S, and then our PT is S. Now this becomes 36 equal to 9S plus S squared. Solving this, we have S squared plus 9S minus 36 equal to 0. Now solving this, S minus 3 and then S minus 12. So which one will be positive? This should be positive, equal to 0. You discover that S minus 3 equal to 0, giving you S equal to 3, but S plus 12 equal to 0, giving you S equal to minus 12. The answer cannot be negative. Therefore, our s minus 3 equal to 0, and your s is equal to 3 units. And that is what is required of you. Our s is equal to 3 units. Example number 4. Here is the diagram for you, described as follows. In the figure above, the line segment ST is tangent to the two circles at S and T. O and Q are the centers of the circles, with OS equal to 5 centimeters, QT equal to 2 centimeters, and OQ equal to 14 centimeters. Find ST, the length of ST. Solution. First of all, we consider the similar triangles in the figure. We find out that triangle OSZ is similar to triangle QTZ. In this case, the ratio of their corresponding sides, OS over QT, is equal to LZ all over TZ, and is equal to OZ all over QZ. You will see that OS is given to us as 5, and QT is given to us as 2. Our LZ is not known, but we are given OQ, so we have OZ. And then QZ will be 14 minus OZ, because we are told that OQ is equal to 14. In this regard, we will cross and multiply. Our 5 multiplying 14 minus OZ is equal to our 2 multiplying OZ. And this will give us 70 minus 5 OZ equal to 2 OZ. And so we have 70 is equal to 7 OZ. Hence, your OZ is equal to 70 over 7, and that is 10. And therefore, our QZ will now be equal to 14 minus 10, which is equal to 4. Using Pythagoras rule, we have that in triangle OSZ, our SZ will be equal to OZ squared minus OS squared, all under square root. This will be equal to, our OZ we calculated is equal to 10, and our OS is 5, and this will eventually give you 100 minus 25, and that's 75, and that will give you 25 times 3, and the square root of 25 is 5 times 3. So you have gotten your SZ. Similarly, in triangle QTZ, we have that our ZT will be equal to ZQ all squared minus QT all squared. Let's leave it as ZT squared. Now, what is our ZQ? Our ZQ is 4 squared. Our QT is 2 all squared. That will give you 16 minus 4, and that is equal to 12. Therefore, our ZT will be equal to the square root of 12, which is 4 times 3 under square root using solid application, and that will give you 2 root 3. Hence, our ST, which we are required to find, is equal to 5 root 3 plus 2 root 3. And that will give us 7 root 3 centimeters. And that will be the solution to that problem. Example number 5. A diameter BA of a circle of radius 6 cm is produced to T, where AT is equal to 4 cm. TS is a tangent from T to the circle, and TS produced means the tangent at B in Y. Calculate the length of TS and SY. Here is the solution. First and foremost, we have to sketch the diagram. From the information given to us, there is a circle, and then of course we have from A to B as a diameter, and then from A to T is 4 centimeters, and this is a tangent produced and is maintained at the point Y, and here from here to here is 6 centimeters, from here to here is also 6, from here to here is also 6. Now with what we have here, carefully let's observe that the first case we are going to treat is to find the value of TS from T to S. As you can see, O triangle OST is a right angled triangle. In other words, we can apply Pythagoras rule. Therefore, we have that our OT squared should be equal to our OS squared and then plus TS also squared. And our OT is 6 plus 4, which is 10 squared. And our OS is 6, which is 6 squared, and then plus TS squared. Therefore, our TS will be equal to 10 squared minus 6 squared under square root, and then we have the square root of that. So this will be equal to 100 minus 36 is equal to 64, and then the square root of 64 is equal to 8 centimeters. So the first value is the value for TS, and is equal to 8 centimeters. For the second part, that is looking for the value of SY. Observe that in the diagram from B to Y, let's call it A, and from Y to S is also A, because the tangent from an external point to a circle, they are equal. That is why BY and SY, they are equal. Now, if you take a look at the entire triangle, triangle BYT, so we now have that in triangle BYT, and this BYT is a right angle triangle. You can see that there. We can also use the same Pythagoras rule to find the value. Recall that your ST is already 8. You have gotten that. So we can have that our A plus 8 all squared will be equal to our A is squared plus our BT. And notice that from B to O is 6, from O to A is 6, that is 12, and then from A to T is 4. 12 plus 4 is 16, so that is plus 16 squared. So you will solve this to find the value of A. When you solve this and to find the value of A, your A will be equal to 12. So the answer to this problem will be for the first one, which is your TS, is equal to 8 centimeters, and then your SY is equal to 12 centimeters. And this is the solution to the problem.